This lesson consists of a description of the internal workings of an affine transform object. Now, I'm going to be showing you a little bit of algebra, and I know some people are allergic to that, so I'm going easy. I'm going to make this as simple as possible. Now, this is not a rigorous mathematical description. This is more of a conceptual explanation. I'll be skipping some of the details, so I can just give you an idea of what's going on in there so you can use the thing. Here's all that's needed to perform a simple translation. To move a point to any other place along the x-axis, it's only necessary to take the existing value of x and add a number to it. In this equation, the starting position is called x and the new position is called x prime. The constant c can be positive or negative depending on which way you want the point to move. The same thing is true for moving a point vertically. The starting value of y has a constant value of f added to it, and results in the new position y prime. With these two equations, any pixel can be moved to any other spot in the window. The rotation of a point about the origin can be done with this simple pair of equations. These equations come from trigonometry, and trust me, given an angle theta and the coordinates x and y, these equations will produce a new set of coordinates named x prime and y prime that are correct for the new location. If there is no rotation, the value for the angle theta is 0, which means the sine of the angle is 0 and the cosine is 1. And that means that x prime will be equal to x and y prime will be equal to y. The point doesn't move. If you want to rotate a point around the origin and move it in one step, you can combine the equations this way. This pair of equations can be used to position a pixel anywhere on the window. It can both rotate and translate in one operation. If this were a math course, I would now go into matrix notation and show you how to work with them that way, but I'm going to skip that part and move on. Ignore that man behind the curtain. Here are some more equations. These are for scaling. If the value of a or d is greater than 1, then each pixel is placed further from the origin. If it's less than 1, then each pixel moves closer to the origin. These two equations allow you to expand and shrink the size of a figure in each direction independently. Okay, once more we skip over a few things. Combining everything we've looked at so far, we can come up with these two equations. The new values of x and y can be derived from the original values by putting the original values through these two equations. The definition of an affine transform, then, is simply the specifications of the 6 values, a, b, c, d, e, and f. This equation form is important. Whenever you give an affine transform object a command to shear or scale or whatever, it just changes the internal values to add that new operation to it. No matter how many operations you have an affine transform perform, it only has one pair of equations using the appropriate magic numbers to transform the x and y values. This means that the affine transform is amazingly efficient. Any set of translation commands can be performed on a coordinate x or y value with 2 multiplications and 2 additions. By the way, the default transform that comes already installed with the Graphics 2D object is the identity transform. In the identity transform, the values of a and e are both set to 1 and all the other values are set to 0. Any values for x and y that are put through the identity transform come out unchanged. When you create a new affine transform object without specifying any of the constant values for it, you get an identity transform by default. In the documentation that you'll find for an affine transform, they don't call the constant values a, b, c, d, e, and f. They call them m00 and m01 and so on. This naming thing is a consequence of the matrix notation commonly used to describe the internal operation of the transform. But you'll see this form in the documentation for the affine transform constructors of Java. This constructor can be used to create an affine transform based on something other than the values of the identity. The values can be either floats or doubles. You can use this form of the constructor to create a final affine transform, or you can build one like this and modify it further using the methods that we've been looking at in the last few lessons. Let me show you an example. This is a program that uses a transform to flip images to their mirror image. Now this is a different polygon than the one we've been using in the previous lessons. To make sure the mirror imaging makes sense, it was necessary to use something that was not so symmetric. This is a constructor of an affine transform. This is the identity transform, so it won't change the figure in any way. The multiplier of x is 1 and the multiplier of y is 1. The figure is scaled up 3 times its size, then it's translated from its position in the upper left-hand corner to a position inside the window where it can be seen. Now each of the 4 figures drawn in this example has its own affine transform. This one sets the multiplier of x to -1, which effectively moves every point to the opposite side of its origin. That is, it creates a mirror image of itself by being rotated horizontally. The figure is then scaled and moved out into the window so it can be seen. Notice that the translation of the position along the x-axis has to be a negative number. That's because the fundamental transform reverses all of the x directions. Now this one is the same as the previous transform, except this time the figure is rotated vertically instead of horizontally. And in this example, it's the vertical translation that has to be a negative number. In this example, both the x and y multipliers in the original transform are set to -1. That means the figure will be flipped both vertically and horizontally. Here's the result. Now this shows 4 versions of the same figure. The one in the upper left corner is the original form of the figure. The others have been flipped to a mirror image. The one in the lower right has been flipped both horizontally and vertically. You can flip an image around any line you like by first rotating the image, then flipping it, then rotating it back. And all of these operations can be defined as a single affine transform.